Welcome, everybody. Great to have you here. I'm really excited to talk to you all. Abner alluded, I'll be speaking to you all about everyone's favorite topic. Everyone loves to think about this all the time, which is manual memory management. And despite how, I know, like, good thing I'm first thing in the morning, right? Hope everyone had their caffeine. So despite how boring that may sound, this is something that every programmer, systems programmers, but all the way up to higher level languages, they need to at least be familiar with this problem, and knowing how you would approach the problem at a lower level will even improve you as a programmer at the very highest levels. So that's what I'm here to talk to you about today. So I'll get started with an audience poll. Go ahead and raise your hand if you believe yourself or have ever been told one of the following things. I got to zoom in here. Manual memory management is complex and difficult to do correctly. Manual memory management is bug-prone. Manual memory management leads to memory unsafety. It's extra effort for no tangible win. Garbage collection, automatic reference counting, RAI, etc. are required to address this problem. And memory management is only relevant for low-level systems programmers. How many people have heard that from a coworker, teacher, etc.? Right. OK, yes. Everyone should raise their hands. Right? These are things that everyone is told from day one of learning how to program. And I was told those things too, originally, when I first started programming, until I was introduced to Handmade Hero. And the host of Handmade Hero, Casey, he would say things like, people don't usually believe me when I say I don't spend time thinking about memory management, and I really just don't. Most of the time, it seems like it just handles itself. And so when you're coming from a perspective informed by statements that I had at the beginning, you hear Casey, who clearly knew what he was doing and everything, you hear him say stuff like that, and you're kind of like, what in the world is he talking about, right? It goes against everything we're told from day one. So I was really intrigued, and I dug into Handmade Hero, and throughout my time watching it, and throughout my time working on a bunch of projects inspired by Handmade Hero's philosophy over the next few years, I learned a bunch of techniques that I thought were really useful for me in basically getting me to the point that Casey was when he recorded this. Like, I don't think about these things really anymore. And I think the techniques can be pretty simple. Like, I don't think they're as hard as people might think. So I'm here to tell you all about them today. Handmade Hero's approach was to start from first principles, right? Understand from the ground up. So let's understand memory from that perspective and see what we can come up with. So this might be a diagram that people have seen before. This is how, if you've taken a computer science program at a university, you've probably seen something like this before. This is like a logical circuit diagram for what's called a flip-flop. Now, I'm not a hardware person. I don't know where this shows up. I don't know if it's probably not used everywhere, right? There's probably subtleties in how how the concept of memory is implemented in different circumstances. But the effect that this provides is the important part that I want to get at. You'll see that if you imagine this circuit flowing from left to right, that it has a distinctive shape, which is that this circuit loops back in on itself. Right? So it retains a stable state, and it can either be in one of two configurations. Right? It could be returning sort of high on the state wire going out, or it can be returning high on the not state or the flip state wire. So this is called a flip-flop. There's a lot of different ways to build one, but this is just like I Googled a diagram of a flip-flop, and this is like what the first one I found. So I was like, let me just draw it in Milton and then put it on a slide. And that implements the effect of one bit, right? Which a bit is just capable of encoding two different, or one of two possible values or one of two possible states, right? And with every additional bit we add to sort of a group of bits, if we consider multiple together, each bit multiplies the number of possible values we can encode by 2. Right? So if you have n bits, you get 2 to the n possible values. Why is that important? Right? Why do we care? Well, in 2014, Mike Acton gave this wonderful talk. I got this screenshot from a very wonderful moment in the Q&A session. I just thought it was very, very good. So in that talk, he explained the following idea. Right? All computation is expressed as data transforms. Right? You start with some input data, and through some computational transform, you produce some output data, so A to B, and that's like a high-level model that can sort of apply generally to everything computers do. But on computers, What are A and B, right? Well, those are implemented through data which is stored in memory. So that's why we care about encoding things into memory. Every single code path you ever write looks like A to B. And so if you're a render programmer, all you're doing, like your A is the game level state, and your B is the frame buffer that you're producing. If you're a gameplay programmer, your A is the game state at time 0, and then your B is the game state at time 1. If you're a UI programmer, it's the application state on the left, and then the UI data structure on the right. And if you're writing a compiler or a parser, you're starting with text on the left and then producing an abstract syntax tree on the right. And all of those things are stored in memory. And then a computer just transforms that, right? And if we dig like one layer down, you can imagine sort of projecting each side of those arrows into like sort of a spatial representation. Obviously, not like to scale or anything, obviously, but every single one of those things ends up in memory somewhere, right? Out of this big pool of available memory on a computer. And now a couple of things are interesting when you look at it from this angle. First of all, I can use the laser pointer. The code itself requires memory, right? So that ends up there somewhere. A and B can also overlap, right? You have like the game state. There's a tick code path that just like applies transform to the same memory. And then everything else, just reads from one and then writes to the other, right? And then obviously these could overlap in more subtle ways, and everything is very high level. But so if we zoom into one particular code path, what does it look like, right? Well, I mean, we actually got to see a little bit of this with like the first part of Kaze's video. But I mean, like you grab memory from some address, you apply some transform locally on the CPU, and you store it back to some other address. Well, what is an address, right? Well, most people will tell you that it looks like this, right? And this is like a fine starting mental model, where an address is just a number. It's also encoded as data, and it refers to some unit of memory. People will tell you that the ordering is linear like this. So if you have 0, refers to the first byte in physical memory, 1 goes to the next byte. People tell you to think about memory as maybe like a big array of bytes, right? And so if you take that model, you can imagine also looking at that code path, it would grab 8 bytes from some 8K, like address 8K or whatever, compute some transform on those bytes, and then store those 8 bytes back to some different address, right? Some destination address, right? 16K. But on modern CPUs, this is not really totally the full picture, right? Because you can also consider that mapping could be something very different, right? Each address could go to some completely different place in physical memory that you wouldn't have otherwise known. And so what we call on the left is like this virtual address space concept, which is, it's sort of the space of all possible addresses that you're talking about. And then on the right, you have like physical memory. And before every time the CPU will take an address that you've written into your code, it'll feed it through this mapping and produce, from your virtual address, as they're called, it'll produce a physical address. And that's where it'll actually load or store things. And now you might wonder why people decided to do that. And there's a lot of good reasons. But first interesting detail, right, is that a virtual address space tends to be, like on all your laptops, for example, it's going to be 48 bits worth of possible addresses you can use. And I told you, n bits gives you 2 to the n possible values. So 48 bits gives you 2 to the 48 possible values, which is enough to refer to about 256 terabytes of memory. Now, you may be a little confused, right? You're like, I didn't put 256 terabytes of memory in my machine. I put 2 RAM sticks, each of which were 8 gigabytes or something like that. And so the physical memory side has a much more constrained limitation on it, right? And so why would people do that? Well, it gives flexibility, right? Because each address space considered independently, someone, the operating system, can make decisions about which portions of addresses you're talking about, how and where they're reflected in physical addresses in physical memory. And then other pages, like maybe something that you're not accessing very frequently inside of your program, those things can be paged out to disk, right? And so you can see there's a very clean division between these two address spaces. The operating system is sort of managing one process, which only has one address space. It can only talk about addresses in its address space. It can't like talk about this thing over here. But if we consider within one single address space, what's the problem? Well, if you just throw everything you know about programming out the window and consider what I've told you so far, all I've told you is that people read from addresses and write to addresses, right? And there's some obvious problem with that, which is that if two pieces of code run together that were not written to run together, what happens? Well, my code could grab some memory and write to some memory. Your code could grab some memory and write to some memory. We wouldn't have planned that that would actually lead to any sort of conflict, but it did, right? We just stamp over each other's work, and that obviously will lead to problems. Which means what this ends up requiring is that any code which would have looked like this, right, where you just grab some pointer, start writing to it, that has to turn into this, right, where every address, you don't know the addresses, they're not resolved statically. You have to go to some shared allocator layer and allocate it dynamically. Now, you don't really care where the base address is. You just care about how much space you have, and the allocator has to care about that, so that it doesn't give the same regions of memory out to other people. So that's like the first example of memory allocation in this like bottom-up look at things. And so far, doesn't look that different. I mean, sure, people would be like, oh, I don't like the syntax or whatever. But so far, it's not that much more complicated, maybe, than like a scripting language, right? You just grab X, start writing like some array, start writing into the array, and then you forget about X, right? Like in a garbage collect language, you can just kind of do that, right? So what's the issue here, right? Why is memory management considered so complicated? Well, as it turns out, both address space and physical memory are not like, infinite, right? You don't have infinite storage capacity on your computer. And you can run out of either virtual address space or of physical memory. The operating system might just kill your process. Now, it's worth noticing that sometimes it doesn't matter. So this is an email from, I forgot the person's name, Kent Mitchell, I believe. Kent Mitchell. It was an email, but I found this on Raymond Chen's blog. And the title of this post, if you can't read it, is An Amusing Story About a Practical Use of the Null Garbage Collector. And what in the world is a null garbage collector? Well, long story short, Kent Mitchell, who is a consultant, was working with like a weapons firm. And he was doing some analysis on this onboard missile software. And he was a little confused because he was like, look, you guys have all these memory leaks on your computer, right? You're allocating things and never getting rid of them, never reusing that memory. And the chief software engineer was like, well, yeah, because why would we? There's enough memory on board the computer, on board the missile, to last, if we leak, this many bytes per second or whatever, we put up enough onboard memory to last the entire flight. And at the end of the flight, there's no computer, right? It doesn't matter. It ceases to exist. So, that was a very practical thing, right? It's no, we don't care about releasing things. We're trying to hit a target, right? So sometimes you can act like this, right? Now, remember, most of us don't write software for missiles. But remember how I told you earlier that this address space deal, that's all managed by the operating system. How your address space translates into the physical resources of the computer, that's managed by the operating system. So when your program crashes, or when your program naturally closes, the operating system knows everything you had in memory and where. So if you allocated all this memory and didn't free it, not an issue. The operating system was already going to clean that up. So that already happens. And so what that basically means is you can treat your program ending as its own little sort of null garbage collector, right? That's number one. But, what if we're not in that situation, right? Because obviously, that's not every situation. You can't just leak forever. And when that's true, this concept of the lifetime emerges, right? You have some alloc, which is what I've introduced already. And because you can't, if you stop accessing that memory, you don't need it anymore. If you do, then you just run out of resources, you've got to scale back your problem or something. But generally, you can reuse things. And so the alloc, one way to solve it would be to introduce a symmetric free. So for every alloc, you have some release, and then the time span between those things for any individual block of memory could be considered a lifetime, right? So an extreme usage rule would be every allocation you ever do, you call alloc, and then you just release it at the right time, right? And so if you follow that rule to the extreme, you end up with code like this. And every single possible thing in your program that could be dynamically allocated that you can't like statically know about ends up with this alloc and release, right? You just get these pairs of functions that look like this. Now, just as an aside, this is all the stuff that garbage collection and automatic reference counting and RAI, they're trying to automate code that looks like this, right? But this rule taken to the extreme is where the complexity of memory management comes in, right? Again, that's the problem that garbage collection is trying to solve. You might think that when you adopt that pattern, you're sort of just having this timeline of various lifetimes, and then you just alloc and release, and then everything's good, and then time flows on as normal. But it's not like this is not a totally complete picture, right? Because also each one of these lifetimes depends on other lifetimes. And so what you get is this sort of web or graph of lifetimes that you constantly have to upkeep as your program continues to be developed. This isn't something that you like write all the allocs and frees once. It's something like you have to worry about all of the allocs and frees occurring at the appropriate times throughout the course of a project's lifetime, right? So you can imagine in a case like a simple parser, on the left-hand side, right, A to B, we start with text, produce a tree of nodes or something like that, like an abstract syntax tree. You have some parsing code path. It'll produce a structure that looks like this. You've got some node struct, and then the visualizing the structure on the right-hand side looks like that. And every single one of those nodes that you didn't know you needed initially, like in other words, you needed to dynamically allocate for, every single time you call alloc, you've introduced some hidden constraint to your code where release has to also be called at some point, right? And this sort of requires like constant maintenance, right? You have to write all of those free encode paths. You have to make sure they don't happen at inopportune times. And if you fail to do that, then you'll run into a bunch of correctness issues that are very subtle and difficult to catch. Some of the problems you'll run into are sort of the ones that, like, if you've ever spoken to like a Rust programmer, they'll tell you, like, you maybe only talked about the issues with them because it's kind of what they bring up, right? And they're things like, first of all, you've got the memory leak, right? You just have like, you've allocated something and you stop accessing it, and it never is reused. Like, it's just like lives on forever. You just have a leak. You could also have a use after free, right? Where you did remember to release something, other code was not aware of this fact for some reason, and it like tried to read or write to that pointer, right? And you can imagine how that gets especially bad if someone else allocated that same block of memory that you're trying to reuse, but like some other code path thinks it's like this still allocated thing through like a dangling pointer, basically. And then there's things like, there's more subtle versions of that, right? You have the double free case where it's like, oh, A was allocated, someone remembered to release it. Some other code path thought it had the responsibility of releasing A, and so it did the same thing later, but before that happened, like someone else allocated the same block, and so you get this like double free kind of thing where the orange part of this was allocated by someone else, and they expect that memory to be around, but someone else just went and freed it underneath them. And so it's kind of a big issue. Other things occur with this kind of approach to memory management, right? Over time, your like available memory store can become very not corrupted, fragmented, right? You start with like maybe just like filling the available space you have, and then you might free individual small chunks of that memory such that you have a bunch of space available. None of it's just contiguous, right? You have all this like these little chunks of memory that you can't fill because they're like too small to be useful for a bunch of cases, right? And so alloc and release, that concept is implemented in the C standard library through these two calls, right? Malloc and free. And keep in mind that the possible implications of malloc as a sort of interface right? Being able to alloc and release at whatever time works for you means that, like, in a case like this where I'm allocating these 4 like blocks of memory, I can sort of allocate and free in sort of a variety of orders, right? It has to be ready for any possible combination of allocs and frees that I can throw at it. And what that happens to lead to is like a lot of implementation complexity, right? You have like I went and looked at glibc's malloc implementation. I mean, you can't even read it, right? But I didn't put all of it on the slide. But it's like 5,600 lines of code for like this malloc implementation. Now, obviously, it's like tightly optimized. Like, they've done a bunch of things for it. There are other malloc implementations that are bigger. But, you know, that's like a lot of code. I'm not here to tell you how to write your own malloc, because everyone knows that, I mean, unless you're really interested in this kind of thing, you'll be like, I don't really want to go and do that, right? That's not what you do. Like, I'd much rather use garbage collection, right? This also leads to a problem of, like, the sort of the interface of malloc leads to this issue of, like, contention between multiple threads, right? You have 2 different threads accessing this global allocator, and you know, that leads to advice like don't dynamically allocate in a hot loop, right? Because why would you? You're causing contention between threads. Just don't do it, right? So, quick question. Have you written code this way before? Just like raise your hand if you want to answer. And what issues did you encounter? Anybody want to say anything about that? Right here.
I actually run across that issue with the scalability. So like when you scale like more than I had 4 sockets each like 8 cores.
Yeah.
As it's my first socket, like it built a little bit of performance. Like most of the time spent out.
Oh, I see.
It doesn't scale.
So in your case, most of the time was spent the allocator just because of like the wide scalability that you had in your problem.
Yeah, most would be bad. Like basically you couldn't scale fast. Like the efficiency I got, you know, instead of like you get like 80-90% of something, as far as I get like 30.
Right. Okay, sure. Right here.
I also have problems writing in microcontrollers where a lot of libraries are written with this like malloc thing where we're like, we have a fixed amount of memory. We don't actually want very memory. We want to just like ensure we have enough
Right.
and then run it in a statically allocated way.
Sure.
So like a lot of libraries are written in this way where they just expect that you want dynamic allocation, but don't always want that.
Yeah, for sure. Anyone else want to say anything? Okay, sure. Well, yeah, back there. Yeah, for sure. And you know, that example I used, let me go back a little bit. This example right here of the tree, this is kind of one of the easiest cases, right? Because everything is like clearly scoped. When you free the top of like, you know, if you imagine freeing this structure, you have to do a little bit of things, like you have to free the node, but before you free, you grab the children pointers, so then you follow those, and so on. But for the most part, like, there's a single tree walk that you can do that's like well-defined and will free the entire thing, but it gets way more complicated to actually release structures if it's like a graph or something. Way more, like, it becomes kind of a nightmare, and it's entirely like stuff that you didn't want to think about when you were worrying about your problem, right? So, point being, maybe like this whole, you know, make a giant like soup of lifetimes, maybe that was just kind of the wrong approach. Like maybe that was like the wrong problem to solve. Maybe that was a mess that we didn't have to get ourselves into. And maybe the alternative is to treat things in groups, right? This was also mentioned in the Mike Acton talk. Where there's one, there's many. And you could approach the problem from bundling lifetimes as much as possible, so that graph of complicated lifetimes becomes very small and manageable. So we have an example of this already, which this is the other memory management thing that most people don't talk about when they talk about the problems of memory management in C. There are issues, you can screw it up. In fact, I screwed it up, and you'll see it. You'll see an example of this later in the conference, but I wrote a bug related to this. But point is, most people don't think about the stack. They're like, oh, the memory cleans itself up for you, right? It just sort of handles itself. And if we look at what the stack is actually doing, it has a different sort of interface to this whole problem, right? It's like every local variable you declare is like an alloc, and then the closing brace is sort of like your way of saying, release everything that I declared in this block. And so lifetime becomes not a property of an individual allocation, it becomes a property of the scope. The scope itself is sort of correlated one-to-one with lifetimes. And it mostly just works. Like most people get this right away. You don't have to think about it very often. There's like some issues, right? You can return a pointer to something in your, I literally did this, but for the most part, it's easy to diagnose issues when they happen, and it's also easy to like not make those mistakes in the first place. And so bundling all of these allocations together is like very, very simple. It leads to a very simple implementation if you look at how a stack is actually implemented, or just like the regular stack that you're used to working with in a language like C. If I declare a variable, you know, like 256 U32s, basically there's some stack pointer. It like it uses that pointer for whatever variable I declared. A lot of this is statically determined. And then it just bumps the stack pointer, right? It just like bumps forward. And so you can imagine the stack sort of has this initial reservation with some capacity, and then the pointer starts at the beginning, and then every time you need to push, you just push onto it, right? And so remember that in setting up the stack, like none of this goes away, right? The operating system did have to use a complex allocator to like reserve the correct address spaces and you know, set up the stacks, but it pays the cost once per thread, right? Not once per alloc. So why pay the complexity and the performance and all that stuff? Why pay all those costs everywhere? So imagine this example, right? Foo calls into bar, and upon each scope exit, you can sort of think of it as your own little null garbage collector, right? It's like the missile explodes, your function's gone, everything is popped off the stack, and it'll be reused for something else. So you can sort of treat that as like almost like a mini little null garbage collector, right? So, I mean, the stack is pretty amazing, but you know, why is anything other than the stack necessary, right? What, like, we should have just done everything on the stack, right? But why is that not true, right? Most will say limited size. That's not really true today. So then, like, why use anything else, right? What's the deal? Well, the problems start with this kind of pattern, right? If I am in foo and I want to call into bar that wants to allocate something for me, I can't allocate bar, or I can't allocate stuff in bar because like bar can't allocate stuff. Like it only has a mechanism to push higher. So if it allocates inside of its lifetime, by the time it returns to foo, that allocation is going to be gone, right? This is the lifetime I wanted for stuff, but that can't be facilitated by calling into bar, right? So there's like a workaround, and you'll see a lot of code that does this, right? You allocate stuff at the call side, and then pass in a pointer and say, bar, please initialize this. And that can work, but it stops working pretty quickly. Remember this tree structure I had earlier, right? You want to allocate something complicated like this, like a big complicated graph or tree or something like that. And you know, as it just turns out, initializing code, like code that knows how to initialize a structure, can often be the code that also knows how to allocate that structure. So, you know, sometimes there are sort of like this, there's this sort of web of lifetimes that you end up with, and sometimes that's the correct thing for the problem, right? It's like you can't just get away with a single stack that's, you can imagine sort of trying to pull all of these things into the correct sort of stack position, if you will, but it's like coupled in with your call stack. It just doesn't really work that well. You can imagine like a game level in a main loop. You know, a game level sort of like, you can imagine wanting to like missile explodes, think about a game level when you want to load a new one. But you know, it's like the main loop is implemented in a call frame. Like you're not going to pop out of the main loop and go back. Like what really is going on there, right? Like that wouldn't work with a stack situation. So quick question: what are other reasons you've like just preferred not to use the stack? Like, is there any like time you've been thinking about trying to allocate some stuff, and you've just been like, the stack's not suitable for this problem? Did you, like, if you thought it through, like, what was the reason why? Any show of hands or anything? Right here?
Anytime you're doing like recursive
Sure, yeah. You have recursion right there?
The data is very.
Yeah, yeah. So like I said earlier, the stack in practice, like you can configure it such that it has much larger limits. And it doesn't need to pre-reserve or pre-commit all of the memory, but that is like a lot of code is written with that assumption where it doesn't want to change the stack size or something like that. So anyone else? Right here?
Data that'll be shared between threads.
Yeah, sure. Yeah, cross-thread data right there.
I need to grow my array or tree or whatever.
Right, like growable memory. You don't want to assume a fixed size cap or something like that. Anyone else? Are we good? Okay. So, obviously, one stack has a bunch of limits, right? I mean, it's weird. Like, the stack just seemed perfect, but we just discovered it has all these issues, right? But what if you had, like, n stacks? What if you could just talk about n of them? And nothing is stopping us from writing a concept like that. And that's the whole idea, like, that's the first sort of technique to know from this talk, is this arena allocator thing. And an arena is kind of just like one stack that you name and can refer to by name. And one arena is just sort of like, it's the entity that corresponds to one tree of lifetimes, right? You sort of just refer to an arena, and you're referring to sort of, one thing it refers to is the tree of lifetimes. So the arena lifetime begins upon arena alloc, and then it ends when you like release the whole arena, just jettison the whole thing away, or you can imagine clearing the arena too, like if you want to reuse it across multiple phases or something like that. It could also intermediately pop, right? You could push onto an arena. You could also pop off the arena, but not without clearing the whole thing. And so now, if we go back to that example where foo wants to call into bar and it wants bar to allocate something for foo, it can just pass in the arena and say, I want the allocation here. And that works for everything, right? It works for if stuff happens to be a very simple allocation. It works if it's a linked list. It works if it's like a big array. It works if it's a complicated tree. You just pass in the arena, and then it's like bar knows how to allocate. It doesn't have to push onto its call stack, but it can push on to the past arena. And so our picture, if we adopt that like practice, our picture of A transforms into B gets like one little extra detail when we actually implement a transform, right? We have the result, which is B. We have the input, which is A. And then we have this extra like lifetime parameter, right? Where you say, I'm going to, like B from A requires some sort of allocation, requires physical resources. So here's where I want you to put those physical resources. And so arenas, if you use them as this named concept, you can use them in a variety of circumstances, right? Because you can sort of construct them as referring to a lifetime, you can control the bounds of that lifetime, the properties of it. And so you can use it for a number of different circumstances. You can have frame arenas. There's like a very common example. You can have a per request arena if you're writing like a web server or something like that. You can also just have a permanent arena, which just never resets. You just never free it. And you'll notice that at each of these call sites, like where I'm grabbing B from A, I've already declared where and how this thing is going to be freed just by passing the associated arena, right? And this leads to other benefits too, right? Remember how a single global allocator like didn't play well with multiple threads, like they're going to be fighting over the actual implementation of the global allocator. With arenas, you can dedicate arena. You can dedicate. Okay, is that from me? Okay. I think I'm okay. But with arenas, you can have. You can just dedicate arenas to specific threads, right? And they can just never touch the allocator of a different thread. They can push at will without ever having to be worried about having to fight between multiple threads, right? And so now, what happens if an arena runs out of room, right? The same thing happened with a stack. It's like, you can have stack overflows, for example. What happens if you've pushed as much as you can onto an arena, but you need like some new allocation, and the allocation pointer is just not far enough from the top of the arena for you to push that thing on? Well, there are three options. Option one, you could like stop the program, like you just panic. Option two, you can push a new chunk of memory onto like a linked list, right? You can reserve a new block that's capable of filling the requirements for your allocation, for your new allocation. And then there's this third option, which comes from what I spoke about earlier, where we can take advantage of the fact that what we think of as addresses, right, memory addresses, that's virtual address space. That's not physical memory. That's sort of in this world of addresses. And so we can reserve a huge portion of virtual address space, so something like 8 gigabytes, 64 gigabytes, 256 gigabytes. But that doesn't contribute that much to how much memory we actually have to commit inside of our process. It's just reserving the addresses, right, which is actually much cheaper. And then, when we need to push more onto the arena than we've actually physically backed with memory, we can commit pages as necessary. So, remember, an address space, 256 terabytes. You can simply do something like reserve 64 gigabytes for an arena, and never have to think about it again, because you have 256 terabytes worth of address space. You can also combine options 2 and 3. You can combine these two options. You can have a mixed strategy where you prefer, for example, like reserve commit, like you prefer option 3, but then like only to a relatively lower size. If you don't want to waste too much address space per arena or something like that, you can combine these strategies. But, I mean, there are options, right? So, number one immediate benefit of doing the reserve commit style thing, one like clear thing that just falls out of it immediately, is you can have dynamic arrays. You can grow sort of blocks of memory without ever having to relocate them in address space. And so if anyone here has written C++, you've probably run into I ran into this when I wrote C++ before because I didn't read the docs. But you can have an std vector of foos, and you grab a pointer to a foo, and then you push back, and then later you try to access the pointer. And like that's like not allowed. Like you can't do that. I mean, you could, but you'd have to like parameterize the std vector with a different std allocator or something like that. But point is, like in the docs it says like after you've pushed back, iterators, pointers to things, all wrong, don't use them. But with our arena strategy, I thought I had a slide of it, but with our arena strategy, we can just not do that, right? The address space stays in the same spot. If we push new things onto the arena, commit more pages as necessary, then we just commit more pages. We have access to those. We have access to physical pages backing the initial address space reservation that we made, so you can have just these absurdly large fixed size, technically fixed size cap array, dynamic arrays. The cap just happens to be like 64 gigabytes or 256 gigabytes. And the thing about an arena is that it's actually pretty simple to implement, right? It's just a stack. So this thing, like I pulled this from my code base, and you can implement it in like 200 lines of code, including all like the reserve commit stuff that I just spoke about. And so if we just walk through the API, it might be a little hard to read on this screen, but so I mean, first you have the calls I spoke about earlier, arena alloc, arena release, so that's just if you want to reserve the address space, get it ready for using as an arena, and then you can also just get rid of all the address space to be reused later. That's sort of the malloc and freestyle interface at the very bottom. You can also like, you can also like, set some you can have, an arena could have the feature of like automatically aligning to some boundary if that's important or whatever. And then, all the important calls are basically right here, right? You have these push variants. You can push onto the arena. You can pop off the arena, including like a full clear if you just don't want to keep anything, right? These are like some useful macros that I use for anyone like wanting to do this in C, where you can just like, you don't have to do like, you don't have to do the cast in C anyways, but if you're in C++, you can do the cast here. You can automatically calculate the size, makes it a little bit simpler. One thing that's maybe worth noting is like a convention that I recently started doing is I just push automatically zeros the memory, so you can see like the default is to just 0, and then you can also have a no zero equivalent if you just want to do the push if you know it's going to be filled or whatever. And so how does this look like in practice? Well, it's not that different from the example slides. If I wanted a bunch of string functions that do a number of common string operations, right? Producing a format string, splitting a string by substrings that you want to split on, joining a string list, like something that comes back from a split operation, joining that into a contiguous string with different separators or something like that. All of those, just you can see, they just take an arena parameter, and then you pass whatever arena is required there, and then you're done. Also works for parsers, right? So if you wanted to produce a buffer of tokens given some text, you just pass the arena that you want, and then you get a buffer of tokens back, and then you can pass those tokens into the parsing from text tokens function, and then you'll get the abstract syntax tree back, and you just pass the arena. There's no free call, because by passing the arena, you've said everything you need to say about the freeze, right? And like I said, an arena could be used as a stack, where to do that, all you need to do is remember the arena and the position, and then begin some, you grab that position, and then when you're done in that sort of temporary window, you can end that temporary window just by popping the arena back to whatever position you remembered. And so what you can do with that is if you wanted to use an arena like a stack, so if you wanted it to correspond with your sort of your call stack, then you can just have a couple of thread local arenas that you use for that purpose, right? And you can see me using that in this example, like UI button function that I have here, where I've passed in a format string arguments, right? So I have the char star format, like the C string, if you want to put a format string into a button, which is just a wrapper around this UI button call. And what I need to do is this isn't the string I need. I need to produce a format string, and so I do all the crap of VA list args, all that stuff. Allocate a format string onto a Scratch arena locally, and then I just call the UI button function normally, and then I release the Scratch at the end, right? Oh, I guess I could have used those slides, but there you go. So why use that, right? Why use a thread local Scratch arena at all? You have the stack already. What's the deal? Turns out that if you write all of your code, if you adopt this rule of take an arena when you want to allocate, by having a thread local Scratch arena, you've now sort of exposed the call stack's lifetime via this arena interface. And so you can plug that lifetime into any code that you wrote for an arena. So there's a subtle problem here, which maybe this will get into the weeds a little bit, but I think it's worth covering. Imagine you just had a single Scratch arena, thread local Scratch arena, and you grab it, let's say I'm in foo first, and I'm well, I really need to call into bar to get some stuff, and so I grab the Scratch arena here, and then so I pass in the Scratch arena into bar because I want it to allocate just locally, I don't need it for that long, I just need to do some intermediate computations or something, and I release the Scratch at the end, and in bar, it's oh, okay, so I have this arena I need to allocate on, but I also need a Scratch arena to perform some intermediate computations. And so I'll push some stuff onto the output arena, right, just arena. And then I'll push all my Scratch stuff onto the Scratch arena. And then I'll release the Scratch and then return the stuff, right? So what's the issue? Well, all three of these arenas are the same thing, right? So by the time release Scratch is called here, it's actually popping off all the stuff that went onto this arena up here. And so this is a problem that maybe is best referred to as arena aliasing, right? You have two different arenas, and they're sort of conflicting, you think they're for different purposes, but they're not. So what are the options here? Right, if we want to make this thing kind of work, number one, we can just have a pool of arenas per thread, where once you grab one as a Scratch, can't be used later. Some downsides to it, right? It's more expensive per thread, right? You need n possible arenas per thread. And you can only go sort of n, you can go O of n layers deep in your call stack if O of n frames in the stack use a Scratch arena, right? You can't have super deep call stacks, which maybe you shouldn't anyways, but that's a serious limitation. But there's a second option, which is get Scratch simply needs to return an arena that does not conflict that does not match with an arena passed by the caller, right? And so an example of doing that, right? That's what those two like 0, 0 parameters were in the first example. You can see in this like parsing function I've got, I need a scratch, but I've been passed an arena by the caller because I'm allocating like an abstract syntax tree. And the first thing I do when I grab the scratch is I pass in the arena that it cannot match, that the scratch arena cannot match. And when I push things onto the output arena, they don't match the scratch arena that I had before. Right? So that's like a simple way around this kind of problem. But you can imagine, like maybe you could think that if this function called into something else that needed a scratch, it passed its scratch, there's actually no problem if you have at least 2 scratches in the thread local storage, right? Because if I'm in this call frame, I've got this arena which could have been a scratch for my caller, and then I have this scratch which is a second one. If I call into a third function which also needs to get a scratch, it can also be this one, which is a little subtle and like kind of hard to get into in a case like this. But if I call into a function in here which needed to use a scratch arena, it'll pop everything off above sort of where any results for the caller were allocated. So maybe a little off into the weeds, but you can ask questions about it if you're trying to figure that out a little bit more. All right, so let's get to the big issue. Right, you're like, these arena things sound pretty great, but like there's like a little problem here, right? Like you can't free things out of the middle, right? But as it turns out, it's pretty simple to get around that problem. Even though a block of memory you've reserved for some purpose does have to correspond with one uniform lifetime, there are things that you might have within that lifetime that you want to reuse, right? If you have entities in a video game or something like that, some entity spawns and then it gets hit by an arrow and then it has to despawn and be reused for some other purpose. You can approach that with something called a free list, which if you just have a linked, sort of a pointer to a node in each one of the slots here in this like block of memory, each slot would have a pointer, and you can have a free list where you start with the free list and then it points through a chain of all the free nodes. And if you need to allocate something, the first thing you do is check the free list. And if you want to free something, the first thing you do is push onto the free list. You just set the next pointer and then replace the top of the free list. And then if the free list is empty, then that's when you actually grow the arena. And so here's an example of how that looks like in code. Right, you can see like the sort of allocator I'm using is just the arena together with the free list. I've got this like foo thing, like you can imagine this being like a game entity or something like that. It's got this pointer there. And it's worth noticing like the pointer does not have to be you could just consider this a pointer, this portion of foo as a pointer if it's in the free list. You don't have to necessarily occupy space in sort of the live data structure for a free list, but I just made this case simple, which is what I usually do in practice anyways. But when you call foo alloc, you can see I'm doing that part where I'm just grabbing the free list. And if the free list was not empty, meaning I got something off the free list, I move the top of the free list back one slot, and then I just like zero the struct or whatever I want to do. And if the free list was empty, then I just push onto the arena. You can actually see I'm still using the old convention in this code where I have push array 0. But, and that's when I push onto the arena, right? And then I return foo. And then when I release foo, all I'm doing is pushing this foo onto the free list, right? I'm pointing foo to the top of the free list right now, which could be 0. And then the top of the free list just becomes foo, right? And that's how you release. So it's very simple. If you have one particular type that you just need to reuse slots for, you just do this, and then you have basically a growing pool allocator on top of an arena. And so more sophisticated allocators work in precisely the same way. And if you actually dig into implementations of malloc, for example, they're kind of doing all this stuff. It's just that in most cases you don't need something that complicated, right? So this is an example of another kind of complicated allocator that I wrote on top of an arena, which is sort of this quad tree atlas allocator. And I wanted it to be an allocator, not like a packing function, because this had to be like a dynamic cache structure. where I didn't want to have like serious fragmentation or something inside of this cache. The point is, this is all implemented on top of an arena too. You can see if you look at the interface, I can allocate regions and release them with their own independent lifetimes, but those are all sort of scoped by the arena that I'm using for the atlas, right? And so, what's the point, right? What do we get for all this? Well, I need to come here so I can read the slide. I don't have notes for this part. Dynamically allocating memory now becomes basically free, right? Like, in the common case, you're bumping a pointer and taking it. So all of the performance problems, all the complexity, the complex code paths that certain usage patterns of malloc can produce, you don't hit any of those things. In the best case with the malloc implementation, they're trying to approximate this kind of thing. But with the arena, it's just every case, right? You just have it all the time. Releasing memory is also free. You don't have to walk complicated forests of pointers or anything like that. You just bump the pointer back to 0, or if you do want to release the arena, you have to like pay the syscall cost of like jettisoning the whole thing. But importantly, releasing memory is a per lifetime concern. It's not per allocation. You don't have to worry about every single time you wanted to allocate something, you also have to remember to go and free that thing. And you know, arenas, they sort of become this little thing that you can click into any code path to work for both a stack sort of situation and a heap allocation. So all of the functions you write to an arena can apply to both cases now. Number 5, it's a 200-line implementation of an allocator that you control. It means that diagnostics, logging, and visualization are trivial to go and add if you need to, right? And allocations are already bucketed to a unique ID, right? Which is the arena pointer that you passed in. And I mean, number 6, and this is maybe more philosophical, some people don't need to worry about this, but you don't need, if you can control this level and become comfortable with arenas, you don't need to depend on these complex tool chains and languages. You could use arenas in assembly, right? That's kind of all you need. And you don't need sophisticated language features. You can take much more control over your problem. And even if you are in a sort of higher level circumstance, like you're working with modern languages, with garbage collectors, with automatic reference counting, something like that, you can still use the arena-style techniques to make the problem easier for yourself and easier for the garbage collector when those underlying abstractions cause you problems, like they inevitably do. And so I've got like a demo thing where I can like walk through the code or just like show some of the concepts that I spoke about with like the free lists and stuff like that. So I'll pull it up here. And then if people have questions about how this works, or if they want to see more code examples, I can do that too. But, so it's very simple. I wrote this yesterday. It's very simple. Oh God, this is going to be hard if I'm like, OK. So point is, I can spawn entities, right? And these things just like fly all around. And I can just keep spawning them. And you can imagine like, if this is a pool allocator, I'm just pushing onto the arena right now. I'm not reusing anything yet. One thing I can do is clear all, obviously, because the arenas make that trivial. But if I spawn a bunch of things, and let me slow down the simulation right here. I can select one of these things. First of all, I can drag them around. And you'll see that each one of these things has a string attached to it, right? And a string is kind of one of these things that people are like, this is why you can't use like a simple allocator in a situation like this. But it's like, turns out it's not actually like that big of a deal. This is like dynamically allocated. And I can just change whatever string I want. I can also delete this entity altogether. Just keep deleting them. Doesn't matter. And if I turn on the diagnostics here, you can see, I can't really see, but yeah, so I mean, what I've done here is I've just logged, I've had a visual log, again, wrote this yesterday, it's not that impressive of a log, but you can see like I've got these 3 arenas. It shows you how much I've reserved for them. They're just simple reserve commit style arenas. I don't do any chaining. And I've got 3 of them. I've got one for just like the regular state. It's like there's nothing in there. But the name chunk arena, I'm using that for like sort of discontiguous portions of strings that I just assume a fixed size for. and then an entities arena where I reserved 64 gigabytes, and so far I've committed about 3 kilobytes for all of the entities on the screen right now. And then these red portions are the free list, tracing through available spots. And so if I go back, and if I allocate a new entity, did that work? All right, yeah. So one of the nodes in the free list was just popped off, right? And so I've reused that spot. I didn't need to push anything onto it. I just needed to grab whatever's on the free list. So before I move on, are there any questions about this? Any code that you want to see? Yeah. So what was that? Oh, actually, you know, that might be good for sitting at the computer, yeah.
And we have an extra microphone as well here, so that way people...
That would be, yeah, that would be great.
Here, hold on a second. See if this works.
Oh, does it not work? Okay.
Let's just check. Testing. Does this work?
I think that works, yeah.
Good? All right.
All right.
So for the string array that you had there, you said that you assume a max size for the string, and that's how you keep the strings from interacting with each other, or if I start to grow this one, it won't get into the address space of the next one that is allocated?
So let me show you exactly what I meant. There is a fixed size cap in there, which isn't strictly necessary, but I just did it for the sake of like time and simplicity. The thing that has a fixed size cap are chunks of strings. They're not the strings themselves. And so what you store actually is a chain of chunks that are fixed size, as many as you need, and those do not conflict. It's just a fixed size pool. And I could show what that looks like here. So I've got this, oh shoot. There we go. Oh man, okay, hold on. Let me do one of these deals. Duplicate, keep, this kind of thing. Where did four-coder go? Four-coder, okay. So, can everyone read this, okay, or should I increase the size? I can do light mode, yeah. I can't believe you'd want to blind everyone, but. Okay, so I mean, you lost syntax highlighting, but I mean, there you go. So, you know, actually, I won't do it. It doesn't matter. So, the allocator you're referring to is the name allocator, and what you can see is like when I want to allocate a name, I pass in whatever string has been constructed on some like intermediate arena, right? And when I actually want to commit that to like a stateful thing that I'm maintaining with this like name allocator, what I'll do is I'll just like loop through the portions of the string that need chunks as needed. So you can see there's like a name chunk payload size, and that's 56. And I did that just so like a name chunk could start with 8 bytes to the next chunk, and then the rest of the 56-byte block, or the rest of the 64-byte block, 56 bytes, are used for contents of the string. And so when you try to allocate a name, you just grab how many chunks you need, you loop through them, and at that point it's just a simple fixed size free list, and then you just copy in the portions of the string, and then the thing you actually store is a name chunk list,
So basically,
which is the first, last, and count in total size, yeah.
the name is placed somewhere for some size, but it doesn't reallocate for every single character type. It reallocates for every 56 character type. And
Right.
chunk that goes behind the place.
Yep, and I could demo that. Sorry.
Yeah, sorry, I'm not very loud.
Oh, sorry. So basically, each node in the free list of name chunks is going to be fixed size. So as you type, like, for example, if I made a name that was 64 characters, the first 8, let's just say 100 characters, I would need 2 chunks, right? If there's like 56 useful bytes of payload per chunk, then what I would do is as the user types the the 57th character in the string, I would have to allocate a new chunk and store the string discontiguously across multiple regions. And then if I want to treat that as a string later, then I pay the cost of mem copying into a string when I need to, because that's like free. But you could also do a more sophisticated allocator here. I did a simple version just for this, but if you wanted to have multiple buckets of various sizes, depending on what data you're working with, you can just do that too. And that's kind of why I wrote it the way I did, where I didn't put like a static buffer inside of this name chunk, because you can imagine name chunk payload size being dynamic and having a bunch of free lists, not just one. Just kind of depends on what you want to do. But so if I turn on the diagnostics here, and I turn down the simulation rate, and if I grab this entity and I start so I've allocated like some number of the UI is a little busted, but did you see that red thing pop in here? And so that's the free list. And then if I start like allocating again, it'll pop it off, stuff like that. So hopefully, it's kind of a lame visualization, I know, but I did it like yesterday. But so yeah, yeah, right here.
Is there so my question is like when you're showing the diagnostics, you've got those three arenas.
Yep.
And generally, I would think like code shouldn't know what's calling it. It's like public function or something. How do you avoid like on a multiple person project like everyone just making a brand new arena all the time for like their thing? Like how do you ensure that you don't just look that out to a million things, or is that sort of the point?
So I think like many of those kinds of principles, like sort of the object-oriented style view of encapsulation and not having people access things, like kind of having people interact with this interface, I think it kind of makes sense, but only at like an organizational boundary level. Like it's true at some granularity, but it's also false at another granularity. And so with the projects that I work on, the way that I'll try to organize things is like one person will control an important layer, and that layer will be in charge of its memory allocation. But you'd want that layer to sort of be able to be instantiated independently from other layers. And so anyone working inside that layer will have to know, like, here's where the arenas are, like, here's how I allocate things when I need them, like that kind of thing. And then anyone outside of that, they'll construct their own arenas for their own purposes. But it's going to be at a much less granular level than I think what like object-oriented programming leads you to, where it's like every possible little thing just is that exact principle, right? Where it's like nobody can talk about any details at all. And I think that just I found that to actually work pretty well when people work inside of these like larger layers than like the very granular little objects that you find. So hopefully that makes some sense. But.
So you might have like a module and everything, and that module has like some
Yeah, you can do module.
any global namespace set of like, here's the arenas we use for our stuff.
Yeah. So yeah, it's like it's hard to talk about because like most rules of thumb about that kind of thing, like the granularity of a module is not very clear. And so people will think they're making a module, but in someone else's terminology, they're making like, I don't know, like a tiny little object or something. And those two things are not equivalent. So if you adopt the same rules at both granularities, it like leads to this kind of big mess. But yeah, like at some granularity, I think what you're saying is true. Like inside of this layer, it organizes its memory management plan. And everyone outside of that, like they're not tackling that same problem if they were, they'd be in that layer, right? Hopefully that makes some amount of sense, but.
Yes, thank you.
Yep. Oh, Abner, I forgot to record my screen. Sorry.
You're having your free list.
Yep.
And you're adding to it because you freed some things, and then
Mhm.
you're reusing it, but with smaller sizes. When the sizes don't all line up, are you just, if it's smaller and it fits in there, then you're just creating a new entry on the free list that's smaller?
In the case of the name allocator, or just in general? I see.
Because the name ones are all the same size.
Right. Yeah. So I think in the case of the name, you could have like, for example, there are 56 bytes of payload. You could have a 16-byte string, and in that case, you would just grab whatever like you just fit to that granularity. But the point would be that you would have a strategy for different granularities that you want. So if you did have smaller sizes, like you did have a ton of 16-byte strings that you were worried about, then you would probably have a 16-byte payload, or I don't know what it would be, 24-byte payload of like free list, as well as a 64-byte if you expect like some number of larger ones, or maybe you also have a 1024 byte or that 1018 or whatever. I'm trying to keep the first 8 bytes as the pointer in my head, but the point is you could have various sizes of payload and multiple free lists for each sort of granularity that you want. And then at some point, worth mentioning, I didn't get into this in the talk, but with the virtual address space reservation, the granularity that works at is like a page size. So it's like the generic address space allocator that the operating system provides you works at like page granularity. So at most, at least you have to reserve 4 kilobytes. And then that's also the granularity that pages commit. Now, page size can vary, obviously, but generally it's going to be 4K today. Can change, but you're allocating a page granularity. So if you have, for example, a bunch of strings that are like you expect to be much larger, right? You have strings that are like, I don't know, this is like the contents of some file or something like that, and you expect this thing to be at least 4K, in many cases over. Then it's like, that's the case where you wanted the arena, right? You just have an arena per thing in the free list instead, and then you don't need to do this like slicing up individual pieces of an arena anymore. You just have one for the file or whatever you were working with. So does that make sense? Yeah. Cool. Yep. Right. Oh, okay. I don't know who's doing the mic. Right there. Okay.
So I noticed in your statistics, you have code memory committed.
Yep.
I noticed the memory committed is less than 4K.
Uh,
How was that calculated?
oh shoot, maybe I screwed it up. It might be increments of 4K. Sorry. Yeah. I probably just did the wrong divide there. But yeah. So. Okay. Yeah, for sure. Yeah, you do commit in page granularity. Like you can't commit smaller than a page.
So when you grow an arena, do you ever have to worry about like the data across from the old part of the arena to the new part of the arena? Like, do you ever have to worry about boundaries between the pages, the allocators, the operating system, and hardware, and all of that for you?
Yeah. So I guess for the video, I should repeat the questions, actually. So the question was, do you have to worry about boundaries between, like, I would assume pages? Is that, yeah, so pages on an arena as an arena grows. And the way that will work, so this is, to be very precise, this is about the reserve large virtual address space, commit pages as needed. Do you have to worry about things in between pages? And inside of the perspective of your process, all of those things are contiguous in address space. So if you access like the first 32 bytes at the end of a page and then 32 bytes after that page boundary, that's all going to be mapped by the hardware. Like it might be in different places in physical memory, but it looks to you like it's contiguous in your memory. Like your virtual address space, those things are contiguous. Now what you do have to care about is if you do the chaining approach, then that's like discontiguous in your address space. And so that's when you actually have to care. That's one reason why linked lists work very well with arenas, despite like the memes and everything about linked lists. But in a case like that, if you write your code to just work on discontiguous boundaries, like kind of like what I did with the names, then you write your code that way and it works with this contiguity of your storage. But yeah, in the case of reserve and commit pages as needed, that's all contiguous in your address space. You don't have to think about that.
So just to be clear, like if you needed to grow a string and allocate it to the chunk in your chunk list, you would copy the string to a new place that has no contiguous chunks.
Right, yeah, because those chunks are discontiguous. So I'll push a new chunk, or I'll grab a new chunk from the free list or whatever, which could be in a completely different spot than the first chunk I had or something if I was adding to the string. And so in that case, I would grab like the new characters that I have to copy them into that chunk, and then now my string is sort of spread across multiple things. And if I ever want to treat it contiguously, then you can make a decision of just like, you can either have a complex allocator to try to keep it contiguous, or you can just pay the mem copy cost when you need the string as a contiguous string or whatever. So, yep.
I guess the question is, in this stuff, you have gone part of the way towards a fully sort of malloc generic allocator. How far have you ever had to go to make something equivalent to malloc in your arena systems?
Yeah, so question for video. I've shown sort of like one step towards a general purpose allocator just with these free lists. How far have I had to go to get closer? Have I ever had to go like the full length to a full malloc implementation or something like that? Yeah, so the answer is like I've never had to do the full heap allocation thing. Now, on top of an arena, you obviously could if you wanted to. Usually you know way more about your problem than the implementers of malloc do about your problem. So the thing about malloc, and this is a story that I was considering putting in the talk, but I just omitted it. I wrote an arena once and someone told me, and I was using it, and they were like, do you think you could write a better allocator than malloc implementation, like people writing on glibc, or people working on glibc's implementation of malloc or something. And it's kind of a weird question because it's like, it's a different problem. Like writing an arena is much simpler, writing a free list for data you know about, and given your expected constraints on your problem, it's dramatically simpler than an arena. So I've never had to even go to the full generic thing because I always know more about my problem. Now, the most complex one that I've done is probably that Atlas allocator thing that I showed, or it's allocating like variably sized chunks that overlap with each other out of like a two-dimensional space, right? That's probably the most complex thing I've done, and it's kind of weird because you're like using CPU memory to sort of track portions of like a virtual texture space, but the same principle would apply to like a virtual, or to dividing up CPU memory the same way. That's the most complicated I've ever had to do. If I ever need something more complicated, like where I truly have this sort of web of lifetimes concept, then usually I'm only worrying about things that are going to cost way more than 4K anyways, in which case I'll just use an arena per thing that I need. So.
Just so that way everyone in the audience knows, my name is Vincent. I'm helping kind of coordinate a little bit of this. If you could give the mic back to me when you answer right, that when the answer is given, I would appreciate that.
Thanks for coming out, Ryan. Really,
Yeah, thank you.
really cool to see you in person.
Oh, thanks.
So I've got 2 questions for you, and I'll ask them synchronously.
Okay.
So the first one's the easy one. When you show the diagnostics in your tool, you got the 3 blue lines. The 3 blue lines are just showing you the stuff that's currently being used out of the arena, right?
Yeah, it's sort of like, there's no, really what it is a rectangle on the screen. Like there's no data to show there, but the only thing, it sort of is just visually representing all of the committed space. And so when I position those red spots in the free list, that I'm like calculating the percentage offset given the base address. Like I'll take the address of the free list node and then take it from the base address of the arena, and then like do a divide between that and the committed size, and then use that to position it on the UI rectangle. So it's like, there's not really that much to the blue rectangles. They're just blue rectangles, but that size is used for like the positioning of the free list nodes.
Gotcha. Okay, so it's not showing you like this is the start address of the arena, this is the end address of the arena.
Right.
Okay.
Yep. It's just committed. Yeah.
Okay. And then, so my second question was, I'm thinking about this in terms of like an entity component system, where in an ECS, you've got entities, you attach components to like an entity, which is a unique identifier that's not necessarily a pointer.
Sure.
Just an integer. But with like in contrast with the arena, it seems like instead of having an entity that's consistent for whatever lifetime, you keep a pointer consistent. Would that be, is that correct?
Yeah, that's generally, I think that's a very useful approach, and that's the way I usually do it is I'll try to keep like pointers consistent as much as I can. So with entities, like if there are empty slots, I'll just iterate over them. But yeah, I don't know if that was like the heart of the question, so.
No, that nailed it.
Okay.
And then so the follow-up to that is, for use cases like this, where you could potentially have, like where you could have components freed at weird spots inside of the committed memory, you kind of can get into cases where your memory's not compacted. So if you iterate it over, you have like maybe big dead bands.
Right.
Is there a way to deal with that? Or?
So are you imagining, just to understand the question a little bit more, are you imagining that every type of component would end up on the same arena?
Yeah.
Okay, yeah. So you could do that, but I think like in a case like that, if I had a bunch of fixed size things that I really wanted to be able to like quickly iterate over them and have the actual memory accesses be very linear in memory, then I would just have a different arena for the different components.
I got you.
Yeah, and then you might still have a free list through them if you want, but it's, then you sort of are trying to keep things that are like alike things together, basically, in memory in that kind of a case. So, yeah.
Thanks. Vincent?
Yeah, so my question is about lifetimes. So you talked about arenas have lifetimes, and that's kind of part of the thought process.
Yep.
But then you also showed examples of query arena, and then you have the string arena. So my question is basically, is the lifetime kind of an afterthought to the purpose of the arena? So do you like, for instance, you have global arena and things like that. So do you think about the use case of the arena, and then the lifetime is kind of like an after effect or the consequence of the purpose of the arena, or is the lifetime always the primary thought process when you think about what arena you want to make, you want to use?
Yeah, sure. So the question was, do you consider lifetimes as sort of an afterthought? Like there are a few arenas in the demo that I had where it's like a few arenas that are sort of, they all kind of have the same lifetime. They're all used for the same thing. So do arenas truly correspond one-to-one with lifetimes? And, or is that like just kind of like an afterthought to what the arenas are used for? And I think my perspective on it is that it's like, it's a constraint solving problem. So you try to bundle lifetimes as much as you can together. Organizing 3 arenas with identical lifetimes is not that much more complicated than doing one. And so but I wanted to keep, for example, all the entities contiguous. There wasn't a really, and I suppose like another thing was like I wanted to independently free the name arena. So there are like these different constraints that work their way into the picture. So it's not strictly like you only have lifetimes, but there are also other constraints you have to be concerned about. Like, do you want these things to be contiguous? Do you want multiple things in the arena or just one? So on. So yeah, it's not like, there's no unifying thing there, but the arena gives you the tool to bundle lifetimes when you can, right? And so that's what leads to the just dramatic reduction in how many lifetimes you actually have to think about. Because yeah, in this case, it's like, instead of having thousands of lifetimes for different entities, I mean, I kind of do, but they're all scoped by these like 3 large lifetimes that I just set up once and then I forget about it. So hopefully that answers the question. Yep.
So back to the module question, I think there's an interesting nuance here.
Sure.
I've dealt with Minidesk and STB libraries in 2 different ways where the module boundary gets really ugly. So
Okay.
STB, for example, has the ability to reroute like malloc and free like calls. They adhere to that standard. That's in the standard library.
Yep.
Minidesk comes along with an implementation for like what an arena would be and what the interface should be.
Yep.
I've also run in my own code. I have like an engine and an DLL that like I want to pass an arena from engine to allocate, but like the code is technically like in a separate actual module. So like those pointers hopefully work together, but like you have this logic, right, for arenas, and you have the pointer to the arena. Is there some portion of that that can be standardized, so all these things that want to talk about arenas can actually talk about them past like the standard library style of malloc and free, right? Is there like a standard set of like, when we talk about arenas, this is the true, like most boiled down set of like headers that we could all agree on?
Sure, yeah. So yeah, with the Metadesk library, that was like our kind of approach at trying to make different arenas click in. Because we had code bases where we wanted to use Metadesk, but we had arenas in those code bases that ideally we could just write all of our Metadesk code, passing our own arenas in. But if someone didn't have an arena and they just wanted to use Metadesk, then maybe we just supply our own implementation or something like that. That was kind of our approach at like abstracting what we thought about of an arena in that problem space. And it kind of works, but you have to have a very similar interface to an arena to be able to plug into it at all. And so really, I think you basically hit the nail on the head though, which is in order for people to, like, you have to agree on something. If you want to include a library that is like written for an arena that you want to plug your own arena into, if they just have completely different ideas about what an arena is, then that's not going to work, right? So there does need to be like some boiled down set of ideas that people would agree on if they want their code to click together. And you know, you could, like, 10 people could get together and be like, this is the arena we're using everywhere, like, you know, and you'll find that in code bases when people just define an arena in like the base layer and then have layers stacking on top that like can just write everything to an arena. Whether there's a push to make that wider than a single team or group of people, it's like, I don't know, not up to me, right? But you know, but certainly that is the nature of the problem. So yeah, oh yeah, and if you want, like, if C's standard library came with an arena and everyone happened to be happy with it, all the C programmers like put their differences aside, which, like, you know, forget it. But if that did happen, then yes, like everyone just could write to that arena the same way they write to malloc and free.
Hi.
Hello. Abner, I forgot to record. Sorry, my screen. I'm sorry.
This is the organizer speaking for the benefit of the camera. Just wanted to mention that we have about half an hour left.
Oh, wow.
So if
All right.
people want to keep asking questions, no problem. But let's imagine that, this, for the benefit of future speakers, so this is why I'm saying this. Let's imagine you run out of questions, and your master class is over, and we're like half an hour early or 20 minutes. That's fine, right? More time to socialize, more time to go to lunch, or you know what I mean? So don't worry too much, although I'm still seeing hands going up. And I also have a question.
All right, sure.
So, using your arena-based memory strategies for my own software project. And it's funny because I'm running a terminal. People can go to terminal.click. I love that domain. Terminal.click, you can see kind of like GIFs of my terminal project. And people who attend the Ham in Boston will also be getting a beta of it later this month. So you can try this terminal project that I've written, this terminal emulator using Brian's complete arena-based system. It's amazing. Right? I can write a program in C, no memory bugs on Windows, Mac, and Linux, native. It's fantastic. But it's not like there's zero problems.
Right, yeah.
One issue that I have encountered is the issue of overlapping lifetimes. You know, like by accident, it's like, oh, this lifetime like outlived the other one.
Sure.
And I guess I don't know if you mentioned that in the lecture, like how would you maybe address that? It's more like a quick mistake to fix. Like, oh yeah, this is overlapping.
Yeah.
But I guess react to that comment, and then also give me maybe, can you be honest about the issues that you do still encounter?
Yes. Well.
Memory management, even when you're using arena-based.
Yeah. So yeah, a useful point here to make in response to that is like, even though an arena is a very useful tool, they're not an excuse to like not be a programmer and think about programming. So you can't get away from everything. It's just a useful organizational tool, right? But it's yeah. So as an example of a memory bug you can have with an arena is if you return to a portion, if you like return a pointer to a portion that gets popped, right? And so I did the bug you'll see Martin's present later is me doing this, but with a stack, not the arena. But same concept, right? You can return a pointer to something higher up on the stack after you've technically popped it off. Might work for a long time. I never caught that bug, but Martin's did. But it's stuff like that can happen. Now there are some tools you can do because there are some approaches you can have to like quickly diagnosing and fixing those problems. Usually I don't tend to find them that frequently, so I kind of don't go this far in most cases. But if you do have something like a leak on an arena, or you have exactly what you said, like dangling pointers or something like that, what you can do with one example, I don't know a way to sum it up, but one example would be like every time you call that get scratch function or arena temp begin, those two functions that like kind of begin a sub lifetime inside of an arena, what you would do that could be helpful is bump to a page boundary, and then when you pop, any pages that you would have pushed over that page boundary, mark them as no access. So you just say to the operating system, like, these pages that I was pushing on, I'm popping them off, so if anyone touches those pages again, I want you to like throw an exception. And you can do that. So, and because it's just this one, layer where you control the allocator, you can simply do that kind of thing. With a memory leak, it's the same thing. You can say like, if the push size or if the committed memory is larger than 256 megabytes, like debug break and like tell me in the debugger, right? And so you can detect things like that pretty easily because you just have that slim layer there. Uh-oh.
I can add one thing. You don't need to do it. There's easier way to do it.
Oh, okay, perfect. So Martin's advice, yeah.
Just some guys that can help you.
Yes.
Automatically, you don't need to manually
Yes.
program the system.
Yeah.
I'm on the page.
For sure. I'm very much looking forward to your talk because I'm terrible about using stuff like Address Sanitizer. But yeah, I mean, but that being said, the Arena being an organizational tool has helped me avoid a lot of the things that you kind of need that stuff for. But I will never say you just don't need them, right? Those are useful tools. It's just that you don't produce as many problems when you do things in a little bit more organized way. So.
Martin just mentioned that you'll be a speaker tomorrow that you can use the Address Sanitizer compiler to catch these things as well. So thank you for that. And so enable ASAM, people. And to be charitable here, again, the memory problems I encounter in my C program after using this strategy are effectively zero. But the keyword is effectively.
Yeah.
Like, it's not exactly zero.
Right.
So there is like one or two issues that we just talked about. So I appreciate the tips there.
Yeah, and I could add one more thing on that. when people talk about like memory safety or memory safe code, I think it's worth digging into what that definition is. So when people say like, you know, I want my code to be memory safe, for example, what does that fundamentally mean? Like, what's the important content, the content in that kind of a statement? It's like, well, you want your code to run correctly with no memory bugs under all circumstances, which means you could have memory safe code in assembly, right? Because you can prove things about the way your code is going to run in all cases. And so you don't need, like, that's the true important property. Now, I'm not saying higher level tools don't help you check for certain cases or something like that. Like, I don't mean to say that. But I just mean it's a problem about correctness in all circumstances. And so, you know, I think that's a useful thing to consider. And when you are organized about how you approach the problem of memory management and see, it's like you just kind of get a lot better at tackling those problems and being able to prove things about the way your code will execute. So.
Last comment, I'm monopolizing a little bit, I'm so sorry. But last comment is, you know, with something like Rust, which does say it's memory safe, and for all the Rust people here know, you know, I like to be spicy in my indie conference. There is a cost that you pay for that memory safety, isn't there? It's like you put it to a straight jacket, it's have to follow the rules of power checker, follow the rules of compiler time memory safety checks, and it's a difficult pill to swallow in order to get that memory safety, whereas with a C program, at least with me, I talk with C, the freedom that you get from C, with most of the memory safety concerns addressed with this strategy, just seems like a decent alternative to using Rust for many of the programs, right? Now we can get into details about like which industry should be using something like compiler memory safety check always on. Maybe there's a question about like should those memory safety checks only be on at certain times? Is that a way that you know you can write language that way? Like, there's all sorts of questions, but I just love seeing that you can still write C and be mostly memory safe, even though it's not 100%. And I am monopolizing, so please have no questions over. Let's go for the others.
I also have the exercises to get through, so I can go through those, because I was going to do those after the demo. So I could just like walk through them for people who are interested in like the sort of problems that I outlined.
Still have 25 minutes, so there's still time for
Okay, yeah, sure, yeah. I'll just get ready to answer, but I'll still. Oh, do you want me to do it right now or?
Raise your hand if you have a question. Raise your hand. Okay, let's address those questions.
All right, sure, yeah.
Hello. So I have a question about performance.
Okay.
And so I feel certain that in most cases you're going to get a speed up, probably a significant speed up. But I'd love to sort of clarify that with some specific examples, if you know what I mean. So yeah, do you have any case studies or examples where you were using, you came to some code, there was heaps of these like mallocs and trees everywhere, you applied this strategy, you got speed up. And if so, what speed up was that?
Yeah, so the question was, do you have any specific case studies or examples about like sort of switching to this arena style allocation thing, providing a massive speed up? And to answer the question directly, for me, I'm not like much of a performance like grind to the metal kind of programmer. So me personally, no, but there was a very good one presented at Handmade Seattle, like I think last year or 1 or 2 years ago, I can't remember. And it was, God, I'm gonna butcher his name, Andreas Fredriksson, I think. And he had the JSON parsing thing where he took like a very popular C JSON parsing library, and which it was, I don't remember which one it was, but it was basically exactly the malloc and free forest style approach to the problem, and a ton of time was being spent in the allocator. And so he just went and replaced that with like a linear bump allocator, which is what you get in the common case with a growable arena, and you can tweak it to make, like if you can like upfront commit or upfront reserve, like you can tweak things to make it better for a particular case after the fact. But it eliminated like a ton of time. I don't remember numbers off the top of my head, but it's you're turning interacting with this like complicated generic general purpose allocator into grab a pointer and then add, right? So it turns into almost nothing in the common case. And so, but yeah, for a specific case study, no, not except for that talk. Like that's the best example I ever saw. I just kind of switched, and for me it was more about correctness and not screwing up. So hopefully that makes sense. I'm probably the wrong person to ask about like performance numbers and stuff like that. But yeah, I think there's lots of good examples out there. So, but that's the one that I remember. So, yep.
It was at least 100% speed up.
Oh, for the JSON one? Yeah, for sure.
About 100% just for switching.
Yeah, yeah, definitely. Yeah, I remember it being huge. It was like a ton of time was being spent just in the allocator. Now, some cases it won't make that big of a difference because, like I said earlier, malloc is sort of best case getting to what an arena would have given you, and sometimes it does, depending on usage pattern, but sometimes it also doesn't. So, yeah. Oh, wow. Yeah. Yeah. Yeah, that's a great example. Yeah, and that's sorry, one follow-up comment on that. I think that's a good example of like how the don't allocate in a hot loop advice makes some sense under some circumstances, but if you like change what it means to dynamically allocate, it actually becomes like much less of a problem, right? And so yeah, good. Yeah, that was a good example.
So my first question was, so can you show the code for the UI that draws the string?
Sure.
Because I'm thinking like if I wanted to pass these sort of name chunks to sprintf or InGUI or something like that, I would have to, would you rematerialize these strings in a temporary arena?
Yep.
Or like a temporary scratch?
Yep.
So you basically run through the thing, allocate a scratch buffer there, and then pass that to InGUI or some other tool.
Yeah, it's my own UI, but it would work the same way. So what I do, you can see it right here. Like when I'm grabbing an entity name, I have this function that's just like, get me the name from an entity, and I pass an arena, right? So I just say like, hopefully it's visible, but I say like name from entity, put it onto the scratch arena, and then I pass in the entity. And if we look at what that does, oh, sorry, this is from a different project. I've got the same thing elsewhere. Shoot. There we go. And you can see it's doing exactly what you just said. It's pushing the buffer, memcopying portions into it, because memcopy is very, very cheap. Like you can pay, especially like there's such a small amount of data that it's like, in a case like this, like these small variably sized strings, it's actually pretty reasonable to do that. So.
And my second question was like, how do you think about arenas as a whole when combined with threading? Do you give like each thread its own set of arenas? Do you have like some sort of arena that has blocks inside it? How would you take this and go wide?
Right.
Multi-core CPUs.
Yeah. So how do you take arenas and go wide? Like how do you think about arenas as they relate to multiple threads? In many cases, it's exactly as you say. Like a thread will be associated. It'll have its own arena that it's going to be pushing onto. Therefore, nobody else is going to be pushing onto it. No contention or anything like that. There are other cases when, for example, if you did want a shared data structure between multiple threads, you might have an arena that corresponds not to a particular thread, but to the data structure itself. And that way, you would have to. I don't have any kind of special arenas where I put locks into it. I just use locking with an arena to implement that effect. So I kind of pull it out of the implementation details there. Because I'm doing multi-threaded stuff anyway. It's like that's the layer where it should be solved, in my opinion. But yeah, kind of exactly as you say, it's like arenas are most coherent when they're used by a single thread at a time. And so that could either be a shared data structure, or it could just be one thread that only touches it. So yeah, that's kind of the idea. There's also other things you can do, like if you expect contention between multiple threads, you could reserve multiple arenas so that you sort of you sort of shrink the probability that two threads will have to contend with one another because they might hit different slots, and each slot has an arena, something like that. So hopefully that answers the question.
Anybody else with a question? All right, so we'll do one more, and then we can try your demo.
Or you mean the exercises?
Yeah, well, you're going to show something, right?
Was I?
He already showed it. You see what happens when I leave the room for a couple of minutes? Raise your hand again for the question. Cool.
All right,
so I just got some kind of newbie questions here.
Sure.
That was the first time I've seen your earlier example, just regular stack memory freeing being like the end bracket.
Sure.
I'm assuming the cost of freeing is not the same as with heap allocation, but like, yeah, can you say more about like, does that have a cost that like we need to like understand?
Yeah, so you'd have to go look at specific implementations of the more general purpose allocators to know. Freeing is generally not free, despite the name. But in some cases, it can be very fast. You know.
Free.
Yes. Yeah. So with an arena, it's what you saw. You set the pointer back, so it's very cheap. You can optionally also, if you've physically committed a lot of memory and you pop all of it off or something, you want to decommit some of it, then it's more expensive, right? Then you have to sort of do this like syscall to like tell the operating system that you no longer want those pages around. But yeah, I mean, when you call malloc or free or any equivalent sort of allocator, they're managing a much more sophisticated data structure. And so when they do, like when you call free, there are it just depends on the strategies. There are tons of strategies they have to like make contiguous two multiple free chunks that happen to be next to each other. Like there's a lot of extra work that happens there. So, but you have to look at the implementation to know for sure. But it generally will be more complicated, yeah.
Gotcha. Just one more question. You're mentioning the difference between like reserving memory versus allocating it.
Right.
And I was trying to like wrap my brain around the idea of reserving. Is that just saying, hey, like we're going to start allocating from this position in memory, for this other arena we're going to start here? Is that using like allocate or something? Or
no. Yeah. So I have a slide in the self-driven exercises that will maybe cover this, but when you reserve address space, all you're sort of doing is telling the operating system, which is managing your address space, that you should not give out these addresses, this range of addresses. So when I refer to this address as a number, up to this address as a number, nobody else should be given those addresses, but you don't have physical resources backing them yet. So you still can sort of like have pointers to that, and you could like that you expect to read or write to at some point, but it has to be backed by physical memory if you expect to like use memory, right? And there is some bookkeeping too. Like reserving address space is not free. It does cost physical memory that the operating system has to manage to maintain which pages or which portions of address space you have reserved. But it is sort of saying like this arbitrary range of numbers is reserved by like that has been allocated effectively. So in the same way, it's actually kind of similar to the Atlas allocator I had. What I was allocating in that allocator that I wrote was not literal portions of texture memory. It was just numbers that look into a range of like basically just an abstract space. Like some Atlas size from 0 to 1024. If I allocate a region out of it, I'm not grabbing any actual memory. I'm just saying, don't hand out this quadrant of this texture space out to someone else. And so address space is very much the same thing. It's like you're just kind of saying, I want these addresses, not memory for them.
Is there like a special command that you're saying, yeah, don't touch this?
Yes. So this is not. You can't do this from like the C standard library. You have to call into functions provided to you by the kernel, which would be something like on Windows, it would be virtual alloc. On Linux, Linux is trickier, but it's going to start with mmap, and then you can also do madvise. Like there are different things, but you can abstract over them, right? You can have the same kind of interface abstracting over both the Windows and Linux equivalent, and then get the same behavior. But Linux is a little trickier, and I usually do programming on Windows. So, but on Windows, it's virtual alloc and virtual free is what you're going to look at. And based on some flags you pass in, you could either ask for backing memory immediately, or you could ask just to reserve the address space, which is just like virtual alloc with a mem reserve kind of thing, and then it's just going to allocate the address space, and it won't do any, like if you try to write to any of those addresses, it'll be like you haven't committed any pages yet. So, yeah?
Towards the beginning of the talk, you mentioned that you have 56 bits of effective address space, but a pointer is 64 bits. What accounts for the difference?
So it's actually it's 48 bits.
Sorry.
Yeah, you're good. I use 56 later, so but 48 bits of address space. The other 12, and that actually changes depending on the CPU and like environment you're in. So one example I think, I don't write code for the switch, but I'm pretty sure based on reading things from people who do, that you have like initially they had 36 bits of address space, and then it got bumped to 38 maybe. So it varies depending on device. Basically, every consumer 64-bit operating system computer you have, like your laptop or desktop or whatever. In some cases, I think phones, but I don't program for mobile either, so double check me on all that. It's going to be something like 48 bits of address space. Now the other 12 bits, I don't know. I think that's like gets into the implementation details that I'm not really familiar with. It could be that the circuitry they have for like mapping virtual addresses to physical addresses just they didn't want to support a larger number of bits there. Not totally sure, but there's a lot of like hardware implementation details to like speed that process up that probably constrains the number of useful bits there.
I think one thing as well is I think on x86-64 there are some addresses you can write to that will just print something to the screen directly from memory.
Oh, interesting. I'm not sure. Yeah, I'm not sure about that. Oh, maybe. I don't know.
Right there at the front, question. You have a question?
So I can comment on that issue. Like, what happens is like basically a multiple of page tables. So the 48 bits is because I think we have all 4 levels.
Oh, right, for sure.
5th level page tables, and that gives you extra. I think there's 5 full entries, so that's 5 full entries per page table level. So multiply that by 2 to the 8.
Yeah.
Yeah. So that's the basic reason.
That makes sense. Yeah, so different levels of page tables is just where the 48-bit number comes from. And I think some CPUs do have a 5th level page table deal. I don't know much about the implementation there, but yeah.
Also, you can have different page size. So
Yeah.
4K, or you can have 2 megabytes on Intel. I think it's ARM has 65K. I'm not really sure.
Sure,
And
yeah.
This is sign extended. So basically, usually the negative address space is kernel, and the positive is the user space.
Oh, okay. Interesting. Yeah.
Since we only have 10 minutes left, would you mind giving an overview of your exercises?
Sure, yeah.
And finish with that, then we can have some lunch.
I'm very excited I got to this part because I have all right. So if you're interested, if I've convinced you that this is worth trying or looking at or something, I've got 7 exercises. The first one is to just fill out this implementation with like a fixed capacity arena. So this would be sort of like malloc a buffer. You could get it through malloc, and just implement each of these calls, and it should just work like the stack, right? That's like kind of exercise number 1. And if the arena runs out of space, just crash or don't panic or whatever. Or no, do panic. Yeah. Exercise number 2. Panic in the program, not like in an existential sense or something. Exercise number 2, upgrade that arena by chaining multiple blocks together. So if you run out of space on the first block, then malloc a new block, and then start allocating from that block. And then if you pop off everything from that block, move back to the first one, and so on, right? Implement the same arena, same interface with the chaining strategy as like a mechanism for growth. And I say here, it should require no API changes at all, but you can optionally use this step to remove the initial, if you see this API, I have this U64 cap there. You can remove that with this step if you want to just make some default assumptions, right? And you can also optionally dynamically enable the feature of chaining just so a user of an arena could maybe be like, I don't want this thing to chain because I'm treating it as an array or something like that. Exercise number 3, just use the MMU, right? Reserve with something like virtual alloc or mmap to look into your platform. And this would be the giant upfront address space reservation and then committing as necessary. Still requires no API changes. You can also dynamically enable it, just like the last step. Exercise number 4, humiliate STD vector. Use your arena from number 3 to implement, in effect, what you would get from an STD vector, except the array will never relocate. So you never have the problem of pointers getting invalidated or anything like that. You just grab a pointer and you're good. And then obviously laugh at C++ with pity. Now, I should add a caveat. I threw this in because I thought it was funny. If you are in a case where you want to use C++, you can implement an STD allocator and pass that in as like in your declaration of an STD vector, I think. I don't do C++, but you can do that. It's much more complicated than just like implementing a simple malloc and freestyle thing or something. It's like a whole deal you have to do. But if you're in that situation, you can do that. Exercise number 5, use your arena to implement a pool allocator using a free list. I cover this, I think, a lot, so it should follow pretty much straight from what I said earlier. And it's a single free list for a single size to get started. It's like the simple case, which basically comes up. It's like the 95% case, I would say, where you just have a single free list for like some type that you want to allocate. And so you only need one free list, just fixed size, very simple. Exercise number 6, just extend your arena with logging, visualization, debugging features that you can optionally like turn on in a debug build or something. You could log things like the caller source code every time you push, record that information, and then record the arena's allocation position over time. So if you visualized it, you could see if there's a leak just visually by like the arena just like exploding out of control. And then take all that data and visualize it, right? Exercise number 7, convert real code, right? You can find a library, find code that you've written, and rethink the problem and its memory management sort of approach, and try to replace it, and then measure all of the things, like someone mentioned this earlier, like measure the difference, right? See how many lines of code get deleted, see how much easier it was to write the code, which is not something you can measure maybe, but it's something you'll be able to feel. And also measure performance, right? Just see how things improve, or maybe they worsen. Let me know. I don't know. It feels like they improved to me, but. And I think that's it. Oh yeah, and one last thing I wanted to say is like, there's some sort of, there's like, one thing that I wanted to comment on is there's a lot of people who think that like arenas are like game dev. Like they're like, game dev people can use arenas, I can't use arenas because I work on something else. And that's like, I'm biased because I like work on games, and that's why I put in this slide to like show all the stuff I work on. But, so it's true, like I learned this from the game development world, I learned it from Casey originally, and so it's very true that it's like this technique is well known by game developers. But since then, I've worked on a lot of other stuff too, and I found the same stuff to be useful. So I think it's a pattern that extends much further beyond game dev, and I wanted to just like stifle any concerns about like, well, I don't want to do game development, or I don't do game development. Is this still relevant for me? I would say yes. So, and that's everything. So thank you. Yeah, appreciate it.